In this section, we'll be looking at integration with reverse chain rule. Now, this name might not be familiar to some of you, but we did differentiate using the chain rule. So we are saying that we are using the chain rule in reverse here. Having said that, all of these questions that we will look at can be solved with U substitution. Those of you who are familiar with U substitution can work rather magically, but you will miss out the understanding behind the scene. How is it that the magic works, and why is it that the algebraic manipulations help us eliminate all the terms that we need to eliminate? So, understanding reverse chain rule helps you to understand how the U substitution method works better. So let's get to it. First example, we have under the integral 2x over x squared plus 1. What do you notice about the numerator and the denominator? How are they related to each other? If you have a lucky guess, you might think that 2x is actually derivative of x squared, and the derivative of 1 is simply 0. So we have the situation where f dash of x is on top of x, on top of f of x. So if you look at the lines on the top right corner there, you have, if you differentiated y being equal to log of f of x, you would have that derivative there. And creating a derivative will lead to the original y, or the original function, which was log of the denominator. Therefore, here we can simply say it's exactly correct. We don't have to make any adjustments because the derivative of log of x squared plus 1 is 2x over x squared plus 1. Therefore, all we have to do is write the answer there with an absolute sign and the plus c at the end. Right, in this next example, we also have similar situation. 3 plus 2 sine of x is in the denominator. What's the derivative of sine? Derivative of sine is a positive cos. The signs match, but the 2 in front of the sine is missing in front of the cos. We would have liked there to be a 2 in front of the cos so that it would match perfectly. That's fine. We can multiply the cos in the numerator by 2 as long as we divide by half in front of the integral. So here's what we would get if we differentiated log of 3 plus 2 sine of x. The 2 is missing, therefore we can put it into the integral and we can multiply the numerator by 2 as long as we divide by a factor of 2 in front of the integral. Therefore, we can write half of log sine 3 plus 2 sine of x plus c. Okay, in front of half. Alright, so far we've seen the situation where we have a derivative on top of the original function itself. The derivative of function is f dash of x and the function in the denominator. What if the f of x was not in the denominator and they were simply on a single line, like so? Here we know that sine square, its derivative would have been 2 in front of the cos. The 2 is missing and the cos is next to it. Alright, so let's slowly build up the picture. Here on the right hand side we've got k times, k is a constant, multiplied by f dash, multiplied by f of x raised to the power of n. Now, what happens to that n? That n and the k are related to each other. Okay, so in fact, the integral of this expression would have been f of x raised to the power of n plus 1. Because when we differentiated f of x raised to the power of n plus 1, the n plus 1 comes in the front By chain rule, we would have to bring out the derivative of f of x and multiply it at the front, and f of x will be reduced by power 1. The n would be n plus 1 would simply go down to n. So the k in our term, in our case here, is going to be n plus 1, but that k may not exactly match. So that's fine. We can always use the same trick that we did. We multiply and divide by the constant that we want there to be in front of the integral, in front of the in the integral. So in our case, we have a guess that y was originally sine to the power of 3. Okay? What would have happened if we differentiated sine to the power of 3? With the chain rule, we would have brought the 3 at the front. We would have multiplied sine square by the derivative of sine itself, which is cos, and we would have got this exact derivative which is under the integral. That's why integrals or integration is sometimes called the antiderivative. Okay, we are basically doing the reverse of finding the derivative. We found the derivative of sine cubed to be this expression. Therefore, the answer to the integral will be sine to the power of 3 with a plus c at the end, of course. Okay, so let's look at the next example. We have x squared plus 5 all in a bracket raised to the power 3 and the x outside the bracket of cube. Notice that x in the front is not raised to the power 3. Alright, so if you work backwards and think, what if I have a guess at the, the answer being x squared plus 5 raised to the power of 4? Okay, what if I start with differentiating x squared plus 5 raised to the power of 4? What would the answer be? It would have been 4 at the front, power of 4 reduced down to 3, but we would have multiplied by the derivative of x squared, which is 2x. So we can do that. We can bring out the constants at the front, and we see here the derivative of y being x squared plus 5 raised to the power of 4 is 8x. What's missing under the integral is a factor of 8. Therefore, we can multiply and divide by 8 at the same time, and we'll have such an expression. Therefore, the final answer would have been 1/8 multiplied by the color-coded answer here, which is x squared plus 5 raised to the power of 4 plus a c. Let's look at another example. Okay, here we have cot x plus 2 all raised to the power of 3. And in the numerator we have cosec squared. How are cot and cosec related to each other? Cosec squared is the derivative of cot. That's clearly given to us in the formula booklet. So we are going in the reverse direction. So we have the derivative and we are integrating, well, we have the derivative on top of the function itself. We can have a guess at what the original function was. May we? Okay, but actually the denominators, okay, so if we think that this is f dash of x on top of x, that's not correct, because actually the the derivative of cot raised to the power 3 wouldn't have been as such. Okay, the derivative of cot x raised to the power 3 plus 2 is 3 times 2 plus cot x square minus cosec square, and this would have been on a linear line. Okay, so we don't have that data. Okay, this is not the numerator. Therefore, this is not the logarithm version. Okay, this is not what we would have had. Okay, and that would have given us, if we had that, the powers of 2 and power 3 would have cancelled out, and this would have been the under the integral. So unfortunately, that doesn't work. Over here, we have to try something different. We have to have a guess that our original y is 2 plus cot x raised to the power of minus 2, because minus 2 is 1 up from minus 3. Okay? Therefore, if we start with that and we try to differentiate that, what we end up with is the negative 2 in the front. Take away 1 from minus 2, we end up with a minus 3, which is what we have in the denominator, power of 3. And then we would have multiplied by the derivative of cot itself, which is negative cosec squared. Now minus and a minus cancel away, and finally we end up with such an expression which can be neatly put down in the denominator as 2 plus cot x raised to the power of 3 in the denominator. So what's missing in our integral here? Comparing these two terms with each other, about this bracket and this expression, the 2 of course is missing. That's fine. Just like before, we can multiply by 2 in under the integral and divide by 2 outside the integral, so that our final answer would have come from the original guess that we had to drive at. Okay, so I showed you in this example that sometimes your original guess may not work, but you have the the knowledge of derivatives to help you figure out if the derivative and the function itself are side by side or one on top of each other. Okay, so let's look at the next example. We have 5 tan of x multiplied by sec to the power of 4. The answer is given to us, 15 over 4. What are we looking for then? We have been told that theta lies between 0 and pi over 2. We have to calculate the value of theta that would give us such an answer. So we work backwards. We look at our table of derivatives. We have sec multiplied by tan, but sec has a power of 4 in it. We can divide, we can break up power of 4 to be a cube and a power of 3. That's fine, because we know sec to the power of 4 would have multiplied and given us sec cube as a derivative multiplied by 4 multiplied by the derivative of inside function, which is 4 tan sec to the power of 4. But, okay, what's the similarity and differences between this function and this? This derivative function here is multiplied by 4, but this answer has a factor of 5 at the front. How do we deal with that? We replace, we can put the 4 at the front and factor of 5 out of the integral and factor a quarter out of the integral as well. So we have to put a factor of 4 over 5 over 4 in front of the integral, so that everything cancels away and works out to be what we want it to be. Integrating this expression, we'll end up with 5 over 4 multiplied by sec to the power of 4. Finally, now that we know what the answer to the integral is, we can use the limits of the integral, substitute them into the function sec to the power of 4, means in the denominator with the power of 4, and therefore we substitute those values of theta and 0. Cos of 0 is a 1 and cos of theta is unknown. Now we have to do some manipulations here and add to the right, putting the answer there and adding 5 fourths to 15 over 4, we end up with 20 over 4, which is a 5. Therefore, we multiply the 5 by 4 and divide it by 5, we'll have 1 over cos equal to, well, first of all, we can rewrite it like so, and 1 quarter equals to cos to the power of 4, and take your fourth root of 0.25, and finally take the inverse cos. Okay, we know that the answer should lie between 0 and pi over 2, therefore there is only one valid answer that could be given. There is no need to find any other values. Okay, so I hope you found this helpful, and I will see you in the next video.